Okay, let's practice with conservation of energy, or just the energy principle itself. Okay, this is going to be problem 51 out of chapter 10. And if you read it, it's got an interesting loading system for a manufacturer. They have a really big spring that release a spring and it shoots packages up a ramp onto the back of a waiting truck. This is a horrible truck. Forgive me. That's probably the worst truck I've ever drawn. But anyway, we've got this truck, and we're going to try and load these packages up to this. All right, now some things we know is we know that the package starts here, and then the package is going to hopefully end up here. And so we need to define some things in this in our system for these two states, this first state and the second state. Okay, so in this first state, we're going to have a delta S0. That's going to be the initial stretch of the spring. Okay, the spring has a spring constant K. And the box is at rest, but we'll just define a V0 for it. And it's at some height we'll call an H0. All right, we'll go ahead and choose the ground to be our reference point for Y. All right, and then over here, we have a V1 and an H1. Now, I could put a delta S1, and sometimes I do, and just call it 0, because one of the boxes over here, the spring is not stretched at all, or compressed. But I'll go ahead and leave it off on this case. Now notice, I'm doing energy, so I don't care about what's happening in between. I don't care about its X position. I just care about the Y position, or its height, because in energy, gravitational potential energy only depends on height. So this simplifies the problem dramatically. Okay, so let's go ahead and list some things we know. All right, the box has mass M, and I know the mass is 2.0 kilograms. I know that the spring constant K is 500. It's a fairly beefy spring. Spring constant 500 newtons per meter. That's the unit for spring constant. Okay, I know that is initially stretched, delta S0, by 30 centimeters, or 0.30 meters. Okay, and then I know, I know that the height of the bed of the truck, so H1, is 1 meter. Okay, so those are things that are given to me. Now, some things that I know by my own system is I know that the initial height, H0, is 0, based on my coordinate system. Okay, and the first question is, how fast is the package going when it reaches the bed of the truck? So it gets up there, and it's probably moving a little bit as soon as it gets up there. So that's our first question. So we're going to try and find this V1. So I've got all my variables defined, and I have what I'm looking for. Okay, so let's go ahead and start. This is part A, trying to find V1. So first, I'm going to define my system to be everything. It generally is often easier to do that if you can. Not all systems you can do that, but I'm going to try and define everything in my system, which means I'm going to have no external work done, and I can simply say that my I'm going to go final equals initials. So I'm going to have K final plus UG final plus US final will equal K initial plus UG initial plus US initial. Now in part A, you've probably noticed part B has a kinetic or a thermal energy because of friction. But in part A, it's not there, so we're assuming everything's frictionless, so we don't have any dissipative forces. So this is my conservation of mechanical energy, because there's no delta E thermal, there's no external work done. Okay, so with that in mind, now I start knocking off or crossing off whatever I know to be 0. Okay, well, the package starts at rest. It's compressed by the spring. The spring is compressed, but it's at rest before I release it. Okay, or right when I release it, it's at rest. Okay, it's on the ground, and that's where my 0 potential energy is, so that's 0. Okay, when we get up here, the spring's not compressed anymore, so that's 0. Okay. And so what I get is that all the energy initially is stored in the spring, and it gets transformed or converted into a potential energy. It lifted it up a certain height, and it's probably still moving at that point. Okay, we can assume so because that's what the problem's asking us for. So we can now use this to solve for K final. K final equals US initial minus UGF. And rewriting those in terms of their definitions, 1/2 mv1 squared equals 1/2 k delta S 0 squared. Subtract UG final is mgh1. Okay. All right, so now we can solve for this v1. Multiply everything by 2, divide by m, and take the square root. We get v1 equals the square root of k over m delta S 0 squared, subtract 2gh1. And if you plug in all your numbers to that problem, you'll end up with 1.7 meters per second, which seems a reasonable speed for a package. That's a smallish package, decent sized spring constant, and it goes up just 1 meter, which isn't too high. So there's not a lot of energy to start, so we don't expect a lot of energy left over. Okay? All right, now we change things a bit. We say that somebody spilled a soda, creating a sticky spot of length dx, okay, delta x. And that sticky spot has a coefficient of kinetic friction. And the question is, does the next package make it up the ramp? Okay. So we've got some new information. We have a mu k of 0.30, and we have this length of this sticky spot is 0.50, 50 centimeters. Sorry, meters there. Okay, mu k has no units. And we're asking, does the next package get to the top? So what variable could we look for? What variable could we look for? Okay, so you could translate that question, does the package make it up to the top, in multiple ways. I can think of two straightforward ways. One, you could say, okay, well, how high does it go when it stops? Okay, so that means we're kind of assuming it's not going to make it up there, so it's going to stop some way on its way up, and we find out where that is. So we're going to look for H1 and then see if that's less than the 1 meter. And if it's less than the 1 meter, then we know it didn't make it up. If it's greater than the 1 meter, then we know it did make it up. Okay. So we could look for it that way. Or we could look we could say, how fast is it going when it gets to 1 meter? Okay, so basically do this same problem over again, only now we need to insert a loss of energy to thermal energy. All right. Now I'm going to go ahead and do it the first way I suggest, is find an H1, but you could do it just this way and almost have the same equation, except up here at the beginning you have to add in your final state a change in thermal energy and see how does that work its way down into this equation. Okay, so I'm going to do it the first way. I'm going to say, how high up is it when it stops? So I'm going to look for H1 for case B. All right, and which means V1 equals 0. So that's the second case. All right, so I'm going to write this down now. Still going to choose the system being everything, including the sticky spot, which means when I write this out, K final plus UG final plus US final plus delta E thermal, that's our new term, equals K initial plus UG initial plus US initial. Okay, starting with that and thinking about how we did this one, try and solve that one. Try and continue through. Pause the video and try and continue through to solve that one. And see if you can find the final height when it stops. Okay, so let's try. What things do we know to be 0? Well, when right before I release that spring, it's not moving, same as before. It's still on the ground. The spring is compressed, so that's not different. Okay, at the end, the spring is not compressed anymore. I am at some height I don't know, but I'm assuming I stop. Okay, so that's now 0. Okay. All right, so now what am I solving for? I'm trying to find this UG final is going to be equal to US initial plus delta E thermal. Or sorry, subtract delta E thermal. So I subtract this to the other side. So whatever height energy I get, it started from spring energy, but less the amount that was transformed into thermal energy. Now I can put mgh1 equals 1/2 k delta S0 squared, subtract, and our delta E thermal is equal to our frictional force, which is mu kn, times the displacement, which is delta x. Okay. Now that reminds me that I need to think carefully about my free body diagram. Now in this particular case, it's fairly easy to see on this flat spot right here that the normal force must be equal to the downward force of gravity because the box is not accelerating up and down along this flat part before it hits the ramp, okay, which is where the sticky spot is. But I'm just going to be thorough, and this is what I would expect from you. I'm going to draw that diagram out so I can show and develop that habit when the case is not n equals mg, because there are many cases in life where n does not equal mg, so I need to use a free body diagram to figure that out. So F net equals 0, therefore n equals mg. Okay? Which I should say that equals 0, which equals n minus mg. Okay? All right, so with that, this then is mgh1 equals 1/2 k delta S0 squared, subtract mu k mg delta x. And now I divide by an mg, puts it under here, and I get h1 equals a k delta S0 squared over a 2mg minus mu k delta x. Okay, and I've got all those numbers. Those are things I know. I can plug in those numbers, and I get 0.998 meters. So, did I answer the question? Does the next package make it up the ramp? The answer is no, barely. It barely can't make it up that ramp, okay? Because the ramp height is 1 meter tall. So it barely didn't make it. So, nope. All right, and so that is a good example of using our energy ideas, our energy concepts, to convert energy from one form into another via a variety of different mechanisms.